Hello, everyone. My name is EJ Rainville. I'm a PhD student at the Applied Physics Lab at University of Washington, and I'm working with Jim Thompson, Melissa Moulton, and Morteza Darakti. So I want to start today with just telling kind of a short little story, sort of fun when we started thinking about some of this analysis. So I was out with a friend surfing, and we were watching this little bleach bottle kind of drift up near us, and we just watched it get caught in the waves and go right to the beach. So that's sort of what kind of helped remember, oh yeah, this might be an important mechanism for how these buoyant objects are moving around in the surf zone and maybe moving in the ocean as well. So plastics are one major issue, but there's lots of other buoyant objects that we have in the ocean that we might care about. Things like ice, so our Arctic coastlines, little bits of ice, those can be moving around as well. Also in the open ocean, we still have plenty of breaking waves that can start moving ice as well. Another issue is this is sargassum. It's a buoyant algae that's sort of wreaking havoc down in the Caribbean and the Gulf of Mexico. And we might want to know where this goes. As well as marine debris, so talking about hazards, where we want to sort of let people know where debris is washing up after storms, where it's going to go, what might happen to it, things like that. So we had this field experiment also at Duck, so that was a great intro there. So this was part of DUNEX, which is during nearshore events experiment. And we deployed a bunch of microswift buoys. So these are scaled down versions of the larger Swift buoy. Here's some of the local bathymetry in the area. We also had a bunch of other fixed instruments out at that time. So here's those little microswift buoys. There's a few of them out here about to interact with a breaking wave during this experiment. We'll just zoom in on one right here. So they just fit in a little water bottle. They're outfitted with a GPS receiver and also an inertial measurement unit. And so we just go a few different ways, but we get out in the surf zone and we go drop them off, and we're just watching where they were going. One of the original intents of these buoys was to use them more as a wave buoy, as we've talked about in a bunch of other talks. But this signal started popping up and originally was a big nuisance, and we kept trying to get rid of it in our signal. They would get caught in breaking waves, you have big accelerations, and you watch them move really fast. That kind of messes with your accelerations that you're using to try to compute things like a significant wave height. We kept trying to get rid of it, but actually switched our perspective and started looking at it as the signal instead of the noise. So that was sort of a fun transition there. So this is just an example of one of these drift tracks. So we're just watching buoy move along. It's plotted over the local bathymetry. It's moving from offshore to onshore. And when we get into the surf zone, we have these jumps here. It gets into the surf zone, and it goes pop, pop, and it moves right along. So we can see these arrows are pointing in the direction the waves are going and the wind is going. So we can sort of see outside the surf zone, we're moving mostly with the Stokes drift, and we're moving with the wind as well. But when we get to the surf zone, and there's a lot of breaking waves, we tend to jump along. So let's zoom in on this first example. This is kind of a nice example to start with. And now let's look at the time series of the cross-shore displacement from the initial position. So we go drop it off, and now we're just looking at how you move across shore as a function of time. So we see this big jump in position, and I'm sort of following this term jump, following some earlier work that was done on this similar topic where they were seeing these similar jumps in position. And I like that term. So we're following the jumps. So with that, for this particular jump, we can start picking out the average location of this jump. Since we know the local bathymetry and we know the water level, we can get the local depth and the average location of this jump. And from there, we can compute the shallow water phase speed, and this helps corroborate we're probably moving with the wave. We're matching very well with this linear shallow water phase speed. So we get picked up by the wave, jump along, travel for a little bit, and get dropped off again. So with that, we could start to automate picking these out of the whole data set. So over the course of the experiment, we deployed a little over 2,000 buoys. So we have lots of these tracks. Each one has 3 to 5 jumps in it, somewhere around there. Not all of them, but most of them have jumps to some degree. So we can pick these out, pick a start and end time, and start defining some metrics about these events. So something like a jump amplitude, how big are these jumps? How far are you moving in every individual event? And also, how long are you in a jump? So how long do you actually stay on the wave? And we can sort of start to piece together a statistical picture of what these jumps might look like. So here's a distribution of our actual jump amplitude picked out across the entire data set. So across the whole data set, we picked out just over 1,700 jump events. And on average, we jump just over 13 meters on a particular jump. So now if we go and we normalize this by a characteristic wavelength, so during each deployment, we have some offshore mean wave period. We can compute a characteristic wavelength from that mean period and normalize our jump amplitude by that. We get sort of a nice number here. So you jump just over 25% of a characteristic wavelength on average. You have big jumps, a lot of really small little jumps. You just jump for a little bit. But we have sort of this nice 25% of a wavelength. Now, pretty much the same story when we look at the jump times. So on average, we're jumping just over 5 seconds in a particular jump. And if we normalize that by the mean wave period, we get about 78% of a mean wave period that you actually stay on the wave. So these are just sort of some nice round numbers that we can start to piece together on how we might want to include this in some trajectory modeling. So looking at how these are also distributed, so this is our normalized jump amplitude as a function of the normalized cross-shore distance. So outside the surf zone over here, we tend to get not too many jumps. That's not too surprising. We don't have a lot of breaking waves outside the surf zone. Every now and again, maybe something. But we tend to have our largest jump events inside the surf zone. But the large jump events tend to be sparse. Most of our data is concentrated down in this lower region. So around, similarly, that 25% of a characteristic wavelength. We tend to have most of our data centered around that. So we look at this as a function of the error-bearer number, which is telling us something about what types of breakers we have. So most of our data set was in the spilling regime. So we have these nice crumbly soft waves that are a little bit gentler than the steeper plunging waves. So we can't say too much about the plunging, but we do see a bit of a trend when we go to the maximum. So we see that this is pretty consistent in the mean. We don't see much change in normalized jump amplitude as a function of this error-bearer number. But we do see our largest jump events tend to be for small error-bearer numbers, so for these gentle, a little bit more spilling, crumbling waves than for the plunging waves. So a potential hypothesis or explanation for why this could be is you might have this spilling breaker, you might have your little buoy here, and it just kind of rolls down the face in this gentle breaker and just kind of moves along this way. In the plunging regime, you might get kind of pulled up over the lip and get plunged underneath the wave and then pop out the back. So you might, on average, miss actually surfing on these waves. This could be a potential explanation, but we don't totally know this for sure. That's just what we see in those maximum values. So, okay, so now let's try to model some of these trajectories, see how we can start including this. So this is a kind of hilariously simple model for how you move as a buoy. So you move mostly with what the ocean's doing and with a little bit of the wind. So this wind sensitivity epsilon here, if you're talking to some people, they might say that's 3%, but it's generally pretty small. This here was from Wagner et al. 2022, and it described how this wind sensitivity factor changes with your relative density and also with a few different shapes. So if we take our microswift, we end up around 5%, pretty close to the 3% rule of thumb of how you move with the wind. It was kind of a nice round number to start this type of modeling with. So let's see how we do. We'll do some analytical calculations. So we just compute a bulk Stokes drift and then compute a longshore current using a radiation stress gradient. So we have our waves coming in. If we go with only the wind and we give our initial position, we move much further south. If we go with the waves and the longshore current along with the wind, we tend to move pretty close outside the surf zone to what the actual buoy is doing. But again, once we get to the surf zone, for the alongshore current and alongshore current version, we go south really fast in this current, but that's not what the true track does. The true track jumps towards the shore. So nothing too surprising there. We haven't included anything about surfing yet. We expect it to not do that. So let's take a first stab at how we might include a surfing transport. So surfing is inherently a wave resolved process. This is not this is a wave averaged model. We just are moving along with the bulk Stokes drift, with our longshore current, and with our wind. So we need to start adding some randomness in here. So kind of go quick through this, but this is some pseudocode. So you pretty much give it some initial position. So where do I start? And you check to make sure you're not on the beach yet. So while you're not on the beach and you're in the ocean, you just start moving with the Stokes drift, moving with the wind, moving with the alongshore currents. Okay, so now if you hit the surf zone, let's check if you surf. We just use a random number generator, and we use our fraction of braking as well that you can get. For now, I'm just using a few different values, but they're fixed. That's something we can improve in the future. But we just use this random number generator to start saying, okay, maybe I surf on this wave, maybe I don't. If you start surfing, find your local depth, compute your phase speed, and start moving at this 0.78 times the mean period. So you get that mean period from this distribution here, we get that 0.78 from here, and you give it your mean period. And that's all you do. You just move across shore for this amount of time, and then otherwise, you wait for a mean wave period. You see if you catch the next wave period, and you just keep moving with the wind, keep moving with the Stokes drift, keep moving with the current. See if it happens again next time. So let's see how that does. So again, outside the surf zone, now this orange track is on top of the magenta track. They're doing the same thing outside the surf zone. But let's see, as we start to get into the surf zone, we start to jump along, whereas the magenta track goes south and does pretty good compared to the true track. The jumps are not variable yet, so this is just a first pass. We have a fixed 0.78 times the mean period. We might need to add some variability and randomness in our jump size, but for the most part, does pretty well compared to our actual true track. This is adding in this sort of stochastic or random term to this model. So now if we run this across a lot more buoys under the same scenario, see how this does. So this is our absolute difference from the beaching location compared to the true beaching location. So wherever the actual buoy hits the beach, how far alongshore are you away in your modeled version? So for the wind-only case, we end up just under, on average, 1 kilometer away. Not too bad. It'd be kind of a long walk if you want to go find your thing, but you could do it. Now, if we start including our known wave effects, so our Stokes drift and our alongshore currents, we do a lot better. So we start moving with the waves. Now we're only just under 0.5 kilometer away. Now, if we start including our braking as well, in addition to that, we take our average difference and move it much closer to the actual true track on average. So we're adding more complexity and hopefully getting better as we add complexity. So one of the next goals is how do we actually include this into some sort of operational model? This is nice, it's in the surf zone, but we tend to know, you're going to surf towards the beach. It's a pretty narrow region, but as we all know, there's a lot of breaking waves out in the open ocean. They could go for a really long time, and these effects of jumps can really start to add up. over time if you want to know where something goes. So how do we sort of start to implement this type of parameterization into a real model? So if you want to know where something is going to go, it might be important to know. Not sure what happened there, but this also doesn't tell us anything about different objects. We're totally constrained to just the water bottles for this study, and it doesn't tell us any sensitivity about, you know, a large plastic, any of this marine debris, small microplastics, things like that, and how they act differently. It's a really nice starting place and can probably get some framework in place, but I think there's a lot left to do to determine sort of something similar to the wind sensitivity chart that we had earlier on a sort of surfing sensitivity chart that could maybe help you implement this parameterization. All right, tons of people to thank. It was a great project and having a lot of fun working on it. So happy to take any questions. Thanks.